So I want to go over functions a little bit, just a little bit of function notation, make sure that we're all on the same page about how functions work, okay? This is not meant to be an exhaustive sort of look at functions. We're going to look at these things in much greater detail at the end of the course in chapter 6, very last chapter. But it is important. We're going to use function notation throughout the course, and so we better make sure that we're all on the same page. So let's do that. First of all, a function is a rule that maps each element from a set of inputs, which we'll call the domain, to exactly one element in a set of outputs, which we'll call the range. When dealing with functions, we use function notation, right? So it's this thing, we read this f of x, right? And the parentheses here in f of x, they do not indicate multiplication. So this is not f times x, this is f of x. And we think of this f of x as the output when the input is x. So you can replace x with like numbers or letters or whatever, right? And f of x is the output that you get whenever you replace x with whatever you put into the function. You may wonder why we use f of x instead of just calling it y. Like back in your Algebra 1 days, when you were first exposed to algebra, whenever you graphed functions, you didn't actually call them f of x, you just graphed like y equals mx plus b and stuff like that. Whereas later on, as you matured through your algebra experience, you may have stopped calling them y and started calling them f of x. And you may wonder, well, like, what's the advantage of doing that? So there are a couple things that function notation is really nice for. For one thing, if I have two lines and I use y notation for both of them, then there's no way for me to keep track of which line I'm talking about. So, so you might have one line that says, you know, y equals 3x plus 4, and another line is y equals negative 2x. If we have some kind of discussion about these two lines, and then later on I ask, is the point 3, negative 6 on the line? Well, you have no way of knowing which line I'm talking about, right? It might be on one of the lines, but it might not be on the other. For example, 3, negative 6 is on the second line, right? But it's not on the first one. So if, on the other hand, I use function notation, then I can call one of the lines f, and I can call the other line g. And so then when I ask the question, is 3, negative 6 on the graph of f, you know which line I'm talking about, and you know that the answer to that question is no. Okay. Another thing that function notation is good for is that it keeps track of not only our output values, but our input values as well. So, so again, if we simply say y equals 3x plus 4, then later on when we say y equals 7, we have an output value, but we have no idea what input value produced it. But if instead of calling it y, I call it f of x, and I say f of x equals 3x plus 4, then when we say f of 1 equals 7, it's very clear that our output was 7 when our input was 1. So that's another nice thing about function notation. It keeps track of both the inputs and the outputs. And it leads to the following fact that is maybe not obvious when you first look at it, but it is obvious when you look at things like this. So the point AB is on the graph of f of x if and only if f of a equals b. Right? Because that's exactly what we're saying. We're saying when the input value is A, the output value is B. And if that's true, then when you plugged in A for X, you got B for Y. So the point AB is on the graph. Let's do some examples. It says find the following function values. Find f of negative 2. Okay, so if I want to find f of negative 2, then I'm going to look at f of x, and where I see an x, I'm going to replace it with negative 2. So in this case, it's going to be 3 times negative 2 plus 5. And then I can evaluate that, right? I can simplify that using order of operations. So f of negative 2 is negative 1. For g of negative 2, I'm going to do the same thing, but this time I'm going to look at the function g. And everywhere I see an x, I'm going to replace it with negative 2. So I get 3 times negative 2 squared minus 7 times negative 2 plus 1. Now, negative 2 squared, that's not negative 4, that's positive 4, right? Because negative 2 times negative 2 is positive 4. So this is going to be 3 times 4. Negative 7 times negative 2 is a positive 14. So we have 12 plus 14 plus 1, 27, I believe. So that's that one, okay? So that's how function notation works. When you go to graph functions, for all intents and purposes, you can think of f of x as y, if it helps you to do that. But the function notation is nice. Ooh, f of x plus h and g of x plus h. I didn't realize we had a couple more problems. Let's remind ourselves, f of x is 3x plus 5. And g of x is 3x squared minus 7x plus 1. Yeah, okay. So if I want to find f of x plus h, then I'm going to look at the function f, and everywhere I see an x, I'm going to replace it with x plus h. So it's going to be 3 times x plus h plus 5, right? I just plugged in x plus h for x, right? Anyway, we can simplify this. 3x plus 3h plus 5. And then there are no like terms combined, so that's as far as that one goes. G of x plus h is going to be similar, right? This is going to be 3 times, instead of x, I'm going to write x plus h squared, minus 7 times, instead of x, I'm going to write x plus h plus 1. Right? So again, I'm just replacing the x's with x plus h's. Okay? And we can simplify this. X plus h squared is not the same thing as x squared plus h squared. The exponent does not distribute across addition. What you have to do is write this out twice and then FOIL. So foiling this, I get x squared plus xh. Well, I'll get an xh there and an hx there. The same thing. I'm just going to call it 2hx and then plus h squared minus 7x minus 7h plus 1. I'll distribute that 3 and then combine like terms. If there are any. Oh, I don't, maybe there aren't any. Yeah, there are no like terms to combine. So I think that's as far as that one goes, right? We've got no other x squareds, we've got no hx's, we've got no h squareds. So yeah, that's as far as that one goes. No like terms to combine. Okay, so that's that. Here's another example. It says let f of x equals, let f of x equal 3x plus 5. Find x so that f of x equals negative 3. Okay. Find f so that f of x equals negative 3. So they're telling us that they want the output value to be negative 3, and they want us to find what input value will give us an output value of negative 3. In other words, we need to take this negative 3 and replace f of x with negative 3. So we can say negative 3 equals 3x plus 5. What's the input value that gets us there? Well, solve for x, right? So we subtract 5, divide by 3. And there we go, right? So x is negative 8/3. If I'm moving too fast, remember, you can pause the video, you can rewind the video, okay? Yeah, so there's that one. Next one. Let g of x be 3x squared minus 7x plus 1. Ah, looks familiar. Determine if the following points are on the graph of of g. So we want to know if 2, negative 1 is on the graph. We want to know if 0, 5 is on the graph. Well, remember, if this point is on the graph of this function, then it should be the case that g of 2 equals negative 1, or that g of 0 equals 5. So pretty easy to determine if this is the case. If I plug in 2, two squared is 4, 4 times 3 is 12. 14 and 1. That's negative 2 plus 1, which is negative 1. So sure enough, right? So since g of 2 equals negative 1, it must be the case that the point 2, negative 1 is on the graph of g. So yes, the answer is yes. What about for part B? Well, we'd do the same thing, right? We would say, well, what's g of 0? Well, that's just going to be 1, right? So g of 0 equals 1. So 0, 1 is on the graph. 0, 5 is not, right? The answer here is no. Okay. So that's that. When we graph a function, we plot the inputs along the x-axis and the outputs along the y-axis. So as I said earlier, for graphing purposes, you can think of f of x equals 3x plus 4 as y equals 3x plus 4, if it helps. Okay, so here's an example dealing with a graph. It says the graph below represents the graph of a function f of x. It's not the same f of x as before, right? Because this one would have been a straight line, and this is clearly not a straight line, so it's a different function. But it represents some function f of x. It says use the graph to do the following. In part A, we want to find f of 2. Okay, so we want to find the output value when the input value is 2. Well, the numbers are maybe a little hard to see, but this is 0, this is 5, this is 10. So I think these lighter marks are 1. So 1, 2, 3, 4, 5, right? So when x equals 2, so when the input value is 2, the output value is right there. So that's 1, 2, 3, right? So when the input is 2, and the input is 2, the output is 3. So f of 2 should equal 3, right? Part B says find x so that f of x equals -9. Ooh, okay, so we want the output value. This time they're giving us the output value. We want the output value to be -9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So when f of x is -9, so that's the output value. What's the input value that corresponds to it? It looks like -2, right? So x equals -2. Or you could say maybe f of -2 equals -9, something like that. Okay, see if you can do part C and D. Give the video a pause and see if you can do C and D. Okay, here are my solutions. I say f of 0 equals 1. And I would say, when it says find x so that f of x equals 0, I think you have two solutions there. On the one hand, the output value is 0 whenever x is -1. And on the other hand, the output value is 0 again whenever x is +1. So I think you get two solutions. Those -1 and +1 both give you output values of 0, right? Okay. All right. Another thing about graphing functions that you may remember from previous algebra classes is that given some function f of x, we can graph a transformation of the function g of x, right? Which is like f of x minus h plus k, by shifting the points of the graph of f horizontally by h units and vertically by k units. What you have to remember is that h, the sign changes, and with k, the sign does not change. Okay, we'll walk through some examples so you get the idea, in case this is a new concept to you. And I'll give you some reasoning in chapter 6 as to why this is the case, okay? For now, just take my word for it, okay? I promise to explain the reasoning later on in the course. But that's what happens to this function. When you say f of x minus h plus k, it's really just the same thing as the graph of f of x, but shifted h units horizontally and k units vertically, okay? In fact, there are a whole bunch of things that we can look at there are a whole bunch of transformations that we could look at. We can look at what they do to the graph of f. So for example, if you multiply f by a, what that does is stretch the graph vertically by a factor of a. So essentially, you would just take all the y coordinates of the graph and multiply them by a. Or if you have like f of x plus d, that's a vertical shift. You shift all the points up d units, right? Anyway, so I'm not going to read the whole chart to you. Again, this is something that we'll look at in detail later. But you know, in order for me to give you the reasoning, you know, we'll look at the reasoning behind all this later on in the course. But for now, let's just practice. This should be something relatively familiar to you anyway. Like you've done some graphing of functions by this point in your mathematical career, so you should kind of know how all of this works. Okay, so part A, or so number 5, sorry, says suppose that the point 2, -3 is on the graph of f of x. Where would the corresponding point be on the following graphs? Right, so let's say that, so by the way, we have no idea what the function f is. We don't know if it's like x squared plus 5x minus 4 or something like that. I mean, we have no idea, right? Doesn't matter. We should be able to still figure out where this point is going to land, right? So if we have this new function, which is just really a transformation of f, then we should be able to predict where this point ends up, right? So this function is going to shift the parent graph of f 4 units horizontally and 7 units vertically. So we're going to add 4 to the x coordinate so that it moves 4 units to the right. And then we're going to add 7 to the y coordinate so that it moves 7 units up, right? So if the point we're starting with is 2, -3, then the point we land on is going to be 2 plus 4, -3 plus 7. So that's where the point lands. If you wanted to show some work, I guess you could do, I don't know, you could do something like, you know, 2, -3, and you can say, here I'm adding 4, here I'm adding 7, and, you know, and then you get this guy. All right, but this is the final answer. Part B, f of x plus 1. So we're going to take our point to -3, and we're going to subtract 1, right? Because, so remember, when the number is on the inside of the parentheses, you subtract, you change this sign. So here we added 4. Here we're going to subtract 1 from our x coordinate. From our y coordinate, we're not going to do anything because there's nothing out here, right? There's nothing going on. So we get 1, -3 is where that point lands. Okay. So for part C, we're going to take 2, -3. We're going to subtract 4 from the y coordinate. That's going to land us on 2, -7. On part D, when you have a negative sign on the outside of the function, what that does is you're going to change the sign of all of the y coordinates, right? You change the sign of all of the y coordinates. So 2, -3 is going to land on 2, +3, right? You change the sign of the y coordinate. When the negative is on the inside of the parentheses, then you change the sign of the x coordinate. So 2, -3 is going to land on -2, -3, right? So when the negative is on the outside, you change the sign of the y coordinate. When the negative is on the inside, you change the sign of the x coordinate. Okay, and then finally part F. Now here we have a whole bunch of things going on. So we're going to, first of all, so we're just going to apply the transformations using like normal order of operations. So first of all, with my x coordinate, the only thing that's going on is that I'm going to add 1. But with my y coordinate, I'm going to multiply by 2 and then subtract 4. Okay, so 2, -3. First of all, I'm going to add 1, right? I'm going to add 1 to my x coordinate, That's going to put me at 3, -3. Then I'm going to multiply my y coordinate by 2. That's going to put me at 3, -6. And finally, I'm going to subtract 4 from my y coordinate, and that's going to put me at 3, -10. And that's where that point lands under those transformations. I don't think you'll have anything too terribly nasty in these first few chapters. So something like part F might not come up again until we get to chapter 6, when we discuss these kinds of things in more detail. But that's how you would apply transformations, right? If you wanted to figure out where the point lands. Graphically, since this all relates to graphs, let's practice how to do this graphically. So here we have the graph of f of x. Right, so this graph is supposed to represent the graph of f of x. Now, let's use that to graph g of x, if g of x is negative f of x minus 3. So if you look at this, what this is going to do is it's going to shift all of the x coordinates to the right 3 units, and then it's going to flip all of the y coordinates over, right, because it's going to change the sign of the y coordinates. So like here, for example, I have this point is -1, -2. But I'm going to shift it right 3 units. 1, 2, 3. And then I'm going to flip it over, right? Because instead of being at -2, at y equals -2, it should be at y equals +2 because the sign gets changed. So that's where that little vertex ends up. I can do the same thing with all the other points, right? So 0, -1 should end up at 1, 2, 3, +1. -2, -1 should end up at -1, 0, 1, one, +1, so 1, 1. This point out here, so this is what, -9, 2. So we should shift it. We should shift it to the right 1, 2, 3 spaces, and then we should flip it over. So instead of being at +2, it should be at -2. And then same thing with this point, right? This is at 7, 2, but it should go over 3, 1, 2, 3, and then instead of being at +2, it should be at -2. So you can see that the whole thing's been flipped over, right? Which is what having a negative sign out here does. It flips things over vertically, right? It flips them over up and down. So then you just connect the dots, right? So you should get something that looks more or less like that. Okay. So transformations of functions. So we're good with function notation. We're good with transformations of functions, I think. One last thing that I want to talk about with functions are piecewise defined functions. These may or may not be things that you've seen in the past. So let me give you some motivation as to why we talk about piecewise functions, right? So first of all, piecewise functions are functions that have one rule on one part of their domain and then a different rule on a different part of their domain. And the reason we might want to look at stuff like this, just to give you an example, is that most people get paid overtime. Overtime is 1.5 times their normal pay, right? So most people get paid overtime if they work more than 40 hours per week. I'm not sure why I have a dollar sign there. So most people get paid overtime if they work more than 40 hours per week. So if you normally make $10 per hour, then you make $10 per hour for the first 40 hours that you work, and then you make $15 per hour for any time that you work longer than that. And actually, I think once you pass a certain threshold, you make double time. So there, it's even more complicated than this. But let's just pretend that this is the only time that your pay gets bumped, right? So you get $10 an hour for the first 40 hours you work, and then $15 an hour for any time that you work longer than 40 hours. So if X is the amount of time that you work in a week and X is less than or equal to 40, then you will make 10 times x, right? Maybe to make it more clear, if I said if x is the number of hours, right? So x is the number of hours you worked in a week, and you make $10 per hour, then you're going to make 10x dollars, right? So maybe to make it, to give you a concrete example, right? If you worked 6 hours and you made $10 per hour, then you're going to make $60, right? 10 times 6 is 60, right? But that's if you're working for 40 hours or less. If on the other hand you make, or if on the other hand you work for more than 40 hours, ooh, well then you're going to make, let's see, if you work for more than 40 hours, then for the first 40 hours you work, you're going to make $10 an hour. So that's going to be $400 for the first $400 for the first 40 hours you work, and then you're going to make $15 an hour for every hour you work after 40 hours. So I'm going to say x minus 40, right? Because let's say that you work 41 hours. So x would be 41, right? But you don't get paid $15 an hour for 41 hours. You only get paid $15 an hour for that last hour you worked. So it would be 41 minus 40 is 1 hour. So you get $15 an hour for the last hour that you worked. So you get $400 for your first 40 hours of work, right? 10 times 40 is 400. And then for every hour after you work, for every hour above 40 hours that you work, that's x minus 40, you get paid $15 per hour. Let's simplify that. So this is going to be 400 plus 15x minus 15 times 40 is what, 600, I think? Yeah, 600. 400 minus 600 is negative 200. So it'd be 15x minus 200. Okay, so if you work for less than 40 hours, you make 10x dollars. If you work for more than 40 hours, then you work then you get paid 15x minus $200. So if you wanted to come up with a function that tells you how much you get paid for working x hours, then this is the function you would have to write down, right? You would say, well, I make 10x dollars if I work for some amount of time between 0 and 40 hours. But if I work for more than 40 hours, then I'm going to make 15x minus $200. Okay. So that's just one example of where you would need a piecewise function in order to describe some kind of phenomenon, right? There are lots of phenomena that behave in this kind of way, where they follow one rule on one part of their domain and then a different rule on a different part of their domain. Functions that use different rules on different parts of their domains are called piecewise functions, like we said, because they're defined in pieces, right? So I just want to give you one example using that same function we came up with for the amount of money you make. Just one example using piecewise functions, okay? So let's say that f of x is this piecewise defined function. Let's find the following function values, right? Let's find f of 17. So to find f of 17, when you're dealing with a piecewise function, you have to figure out which part of the domain am I on, right? If x is 17, then I'm between 0 and 40, right? I'm not bigger than 40, I'm between 0 and 40, and that means I'm going to use the top rule, right? So f of 17 is going to be 10 times 17, right? I'm using that top rule there. So if I work 17 hours in a week, I make $170. What about if I work 45 hours in a week, right? What's f of 45? So for 45, I'm on this other part of my of the domain, right? X is greater than 40. So I'm going to use the bottom rule for x equals 45. So I'm going to say f of 45 is 15 times 45 minus 200. How much is that? That's $475. So $475. So if you work 45 hours in a week, if you only got paid $10 an hour, you would expect to make $4.50, but you made $4.75 because you got time and a half for the last 5 hours you worked, right? So yeah, so if you work 45 hours in a week, then you make $4.75. What if you work exactly 40 hours in a week? Which rule should you use in this piecewise function? Well, if you're working exactly 40 hours in a week, then you're using the top rule, right? You're using the top rule because you use the top rule whenever x is between 0 and 40, including 0 and 40, right? So again, you would use the top rule. You'd say 10 times 40 is 400. So if you work exactly 40 hours in the week, then you make $400 that week, okay? So that's that. I think that's all I have to say about functions for now. The next few sections are going to be about linear functions, linear equations, linear inequalities, things like that. So I'll see you in 1.5.